It's great to be here again to speak. And so a couple things. One is, I love coming to this meeting every year, but all of you come to this meeting every year because I recognize so many of you, which means I have to give a different talk, which adds different challenges to what we do. So I promise very few repeat slides from last year. But last year I talked about the leadership facility, and they asked me to give an update on it, but it's sort of an awkward time for review. So you're going to get my random musings from which you might be able to divulge decisions I've made about the leadership facility and things going forward. And it's worth mentioning things going forward, including how you advance the slide. Remember when there were keyboards? There we go. Look at that. So I also think it's important to put this up because it's an increasing part of what we're doing, and I don't promise it didn't write any of the talk, or maybe even the majority, but it didn't write all of it. So there is still, the smarter and well-written parts you can chalk up to ChatGPT, and I probably did the rest. So, but I do want to talk a little bit about AI and its relationship to HPC and to what we all do. So again, just in the case that you haven't been to one of these meetings before and haven't suffered through listening to me talk right before lunch before, I'm from Texas Advanced Computing Center up in Austin. We're about 2 hours and 45 minutes at non-rush hour times from here, where we run a lot of big machines for the government and open science community. We put out about 10 billion core hours a year at this point, over a few million jobs. Talk a little bit more about workloads. That's one of the mineral oil immersed cooling platforms that we have in Lone Star 6. And we do this, I try and update the science highlights every year. This year was a big astronomy year because we had the Event Horizon Telescope thing that came out in May last year that we were a part of. If you went this year, you need to not hold the meeting in February. The James Webb Space Telescope we did a lot for. It's not visible on the main campus, but that came online in July. That was an August publication of some of the first data from there. And interestingly, we did this, I use the term we in the exclusive sense, in that I had absolutely no part of it. But we had this forecast that was run in the New York Times in August about the fact that, the way the climate was lining up, it's possible, despite the huge droughts, that California is going to get epic rainstorms one after the other. And so two interesting things. One, that happened last month. They got epic rainstorms one after the other. The other thing is I had no idea we did this, but one of my more dedicated and enterprising staff went and found because if there's anything in the New York Times, somewhere there's a real paper about it, right? So they went and found the paper in Science, I think, that this came from. So the New York Times sort of scans Science and Nature and picks interesting ones to write about. Then looked at the references in the Science paper and found out we had all the data for this on our systems through one of our projects. So I consider that an infrastructure success when we have things like that are not only accurate, always a plus in computational work, but that I didn't have to do anything to make it happen. So that was a wonderful thing. So we did do one new system last year. I talked about it coming a little bit at last year's meeting, but we added a bunch of AMD CPUs, we added a bunch of NVIDIA GPUs. This being one of our smaller systems, Lone Star is sort of it's actually one a lot of you run on or your partners run on, because it is our industrial partner system, but our sort of Texas-focused one. And it lets me do a little more experimentation than I normally do on a big system where we want to be conservative in the interest of making it actually occasionally work. But we ditched Luster, we switched from CentOS to Rocky. It's obviously immersed. We started doing node sharing for the first time, which has actually been surprisingly successful because there's a lot of workload that just can't use 128 cores that people want to slide in there. So we stick 7 of them on a node with VMs, and that's worked remarkably well. We've played with disaggregation, which technically actually works, but the cost models don't at the moment, is my quick take on disaggregation at the moment. That might get better over time when we can use the main interconnect. But but we've been experimenting with a bunch of things on our way to the leadership facility. And unfortunately, my final submission to NSF on the leadership facility is due Monday. And then we have the final design review the first week of April, so I can't really say anything about it until that stuff is approved. So other than, if this meeting was like April 25th, I could have gotten away with it, but not today. So, since I spent my whole talk on it last time, let me say, one, still happening, but subject to act of Congress, which means maybe still happening, but depends on the passing of the federal budget. But if the budget passes and somewhere within 5 months of on time, which it happens 38% of the time in the last 30 years, if you're keeping track of those things, then construction starts a year from tomorrow. And the machine, Horizon, shouldn't say 10x follow-on to Horizon, that's my 2031 slide, but it's a 10x follow-on to our current Frontera machine, 15 megawatts, more data center space, stuff like that. So random insights looking at this. So, these are the questions I've been generally asking, right? So, and by the way, timelines in government speak, right? So the machine will really go online in 2025. But that means we have to order it in 2024 and start the data center construction, customization, which means I have to get it approved now, and 2023 is here, and I've been working on this since 2017, so the timeline has gotten remarkably short versus the previous talks on this, but as I mentioned, in a 60,000 core or so system, 1,000 nodes or so, we can afford to mess around a little bit. At the scale of expenditure, right, machines, $125, $140 million, somewhere in that neighborhood, exclusive of storage. It's got to work. So we have to ask some questions. So the way I've sort of put it is, one, do we need more cycles? Two, do we need bigger machines? Could we just do a lot of little machines, right? The distributed workflows, John was just talking about. Thanks for teeing up a lot of great topics for me, John. And then what do we want to put in them? And then there's some other questions we're not going to get to today, even if we get to the slides I put in the off chance there was extra time, which there never is, but they're there. But let's focus on those first three. And the first one's easy, right? And do we need more cycles? Just look at demand, right? And you see lots of talks about this, lots of talks about adapting to, get more performance out of GPUs or thing, but, we still see the sort of big review for Frontera time is next Monday. Yes, same day the other stuff's due. Brilliant planning. But where we'll hand out about 70% of the time on the machine for the year. We have easily triple the demand. But to me, the more interesting part is on Stampede, which we put up in 2017, and the hardware's 6 years old. It's a mix of Skylake and Knight's Landing. Still have 3 to 4x oversubscription on those at that age, right? So when you'd think it'd be moving anywhere else, there's no place else to go. I'm going to get the compute time that we put out. So there's plenty of demand. We know the AI demand is exploding. We know edge and sort of instrument integrated online near real-time streaming data stuff is growing very fast. So you wouldn't be here if you didn't believe in that we actually need HPC time. But the more interesting question is, do we need to look at really big, tightly coupled machines still, or can we just throw all this to the cloud, or can we build 15 500 node clusters and throw them around the country and solve the problem that way? So let's look, and this gives me a chance to brag and also pull slides out of the annual report. But so let's take Frontera, and so this is for the fiscal year ended September. Right, we ran 12 months, 99% uptime, 95% utilization. We measure everything in node hours on this one. This is a Cascade Lake 56 core machine, 2019, so it's in its fourth year now. This was third year. Delivered about 75 million node hours. We ran 1.13 million jobs, right? So that's a pretty big number, and obviously the machine is divided. That doesn't imply that we need big ones, but let's dive into that a little bit more, and this answers several workload-related questions. But we had 2,000 jobs out of that 1.1 million that used more than 25,000 cores in single runs, right? So tightly coupled, that's 513 nodes, which is the cutoff from the normal queue to the large queue, which is why I have this stat. They ate about 25% of all the time on the machine. So a quarter of the machine was at scales above 25,000 cores. We ran 100 jobs that were at half system scale or bigger, half or full system. We sort of limit those to 12 to 24 hours because obviously of the million jobs, if they were all full system and 24 hours long, I would be capped out at 365 jobs a year, which would reduce my number of jobs by roughly 1.1 million jobs. So we can't do that all the time, but we do it 4 or 5 weeks of the year. We put the machine in sort of 1 or 2 jobs at a time mode and give people the whole system. And there are a lot of jobs that can run. That's a 400,000+ core. I'm going to run it at full system, and so they do exist. And in fact, every time we say we're going to have a week of this time, we get about twice as many people asking as we can accommodate to run in that window. So, and like I said, a few thousand who are running at this more than 25,000 cores. We've had 26 different science teams run at above 250,000 cores at this point. So the large, tightly coupled runs are there. So, but if you look at the rest of it, which not only answers do we need big jobs, but also why don't we burst small jobs to the cloud, which is a fairly frequent question. We have flex jobs that we can preempt and use sort of backfill. They're about 20% of those jobs, several hundred thousand. They use less than 0.5% of the time, right? If you look at the small jobs, which was defined as 1 or 2 nodes, right? So up to 112 cores in this case. At 3, you move from the small queue to the normal queue. So again, that's where I have stats. They're over 300,000 jobs, 30% of jobs. They're less than 2% of the cycles delivered, right? So 97% of our time goes to parallel jobs, 168 cores or more, right? So fairly significant size jobs. And by the way, on Frontera, that's about 6 times the size of Stampede, because it is supposed to be the leadership machine on average. But and we do lots to schedule them in. But if you think about that, if I took off the 500,000 small and flex jobs, the sort of easier to move workloads, and I said, say, bursted them to the cloud or sent them anywhere else where you don't need the tightly coupled stuff, I would run probably exactly 0 more large jobs, and my utilization would go from like 95% to 92%. And that's the only thing I would accomplish by moving those 500,000 jobs away. In exchange for that, we could put the users through expense and hardships to actually move over there, right? So we just run them because it's basically free to run them. So because to run, I mean, last night I was looking when, I was preparing my slides well in advance, about 11:15 last night, and which is much further in advance than normal, but Michelle wanted them by 8:30 this morning. So I wasn't working in the last half hour on them, which is, that's a good sign. But we had 6 jobs in the queue that were over 100,000 cores, right? 2K nodes, quarter of the machine, right? So, I had the next 4 days booked up with full, 100,000 core jobs, but we'll run another 30,000, weaved in there between them as they, we drain the 2,000 nodes to run them. So, for each of those jobs. So, small jobs are free, so we might as well run them. We build the machine to run the big jobs, and the demand is really there. Is the message here. So there is real HPC usage. It's not a bunch of ensembles and throughput. Although there are a bunch of ensembles and throughput, they just run for free. That's it in queue time, if you want more details. So then we get to what should we put in these things, right? And so I have shall we say, more current versions of this slide, but I can't remember which NDAs I break when I use the newest ones. So this is sort of a mid-2022 public set of numbers comparing Ice Lake, AMD Milan on the CPU side, and then looking at the MI250X and the A100s for NVIDIA GPUs. And so when we start thinking about what to put in them, your first thought is, well, CPUs or GPUs? And by the way, if you look through the program, look through the talks we've already had this morning, there's a lot of things about moving to GPUs, which represents a trend we see. And I think one of the things, somebody asked about power at the end of the last talk, right, is that if you look at flops per watt, GPUs are the obvious winner. So it's between 5 to 8 improvement, but if this is in gigaflops per watt, right? So because the fact that we can get 10 gigaflops for a watt on a CPU is by itself ridiculous when you think about it. But it's more like 80 on the Chipson Frontier, right? The big machine at Oak Ridge, and the #1 machine in the world. And it is 20 megawatts, which by the way means the power bill for it is only like between $12 and $14 million a year. So it's a non-trivial amount over the times 5 years for the life of the machine. Still not as expensive as the machine, but it's a fair amount of money. But it's 8 times more efficient than doing that in pure CPUs in last year's time frame. So that's the difference between running for $12 million a year and running for $96 million a year. That's a fairly significant difference in operating costs, right? Over 5 years, that's almost $500 million in the change of the cost to own that machine, right? So now, of course, this is, I say naive cut because this assumes that everything runs at the same percentage of peak. which is roughly speaking nonsense, right? But take 2 orders of magnitude off this, and that's what you normally get, right, on most things. But certainly in terms of peak flops, there's a huge advantage, and likely that's going to translate in some other things, if only everything would work there. So you also notice there's a pretty good, in flops per byte, you obviously want to be lower, right? And the A100 is the closest thing to a balanced machine we had in a long time, and that only 6 flops of compute for byte of memory bandwidth. And you think about that, that's 6 double precision flops, so you need 96 bytes to do that, that have to all be in registers or cached or run at full speed. So, but certainly 20 is not a good number, right? And all the CPUs, roughly equal, all the GPUs roughly equal here. Not trying to pick out specific ones at this point. But there is that, right? So we have a huge power advantage, which drives people to GPUs. And then we have the fact that the codes work that drive people to CPUs. So, which also matters to some people apparently. So, so thinking about where we're sort of going in LCCF, the planning process for this began 2017 when we put together the initial proposal, as I mentioned. We had a conceptual design review in 2020. We had a preliminary design review in 2022. We have the final design now, which means I'm making a lot of charts to see how good our projections were over that time period. And I don't have sort of 10-year time horizon projections like I showed in the last talk, because I can be wrong a lot faster than 10 years, right? I can be wrong in 5 years. But forecasts are an interesting thing. But actually, in terms of sort of core sockets and price per dollar, we haven't been too bad, right? Because our initial assumption was that we'd get about 3 times the per dollar value from processors from when we deployed Frontera in 2019 to deploying this machine in 2025. And so we're sort of more than halfway there, and it seems to be more than halfway true so far. Node costs have gone way up, right? I mean, it's $20,000 to get a wafer through TSMC right now. But a lot of the costs, if you look at Intel and say the AP sockets, right, you see a lot of the cost per node goes up because they said, so at 150 watts of power, we're losing in CPUs, we're losing to these 400 watt GPUs right and left. So bear with me now. What if we built a 400 watt CPU, right? So that was sort of the math there, right? So, so what we've seen is the power per socket has gone up sort of non-linearly, but mostly because they're putting more stuff in it, right? Which also means there's more DIMM channels, which adds to the cost, right? To try and keep the memory bandwidth the same, et cetera, right? So, so we have sort of half as many nodes as I thought we have, but we're getting about twice as much out of them as I thought we'd get in that time frame. So, so yes, power's gone up a ton, but the cost per socket has gone up a ton, so it's not as much as you think, going from 150 watts a socket to 350, 400 watts per socket. Because you're going to buy less nodes to get what you thought you'd get. Well, you're going to have less nodes for your budget, so the power increase isn't quite as dramatic as it would appear just from looking at the sockets, but there certainly is some. NVMe has surprised me a little bit in how fast it's gone down. We're now getting pretty close to the release of like 60 terabyte NVMe drives. If you get suitably aggressive pricing in the 2025 timeline, disks start to make a lot less sense, just having them at all. Ironically, tape still makes a lot of sense because you've got to drain that eventually somewhere. And with tape density still going up, it's just so incredibly cheap to put lots and lots of petabytes of data. That there seems to still be a role for that, but doing the first, let's just say I had a tier that we were going to do in NVMe, and I took the next 2 tiers and put those in NVMe too, because there's just no real cost savings in doing it in disk at this point, and the performance difference is so dramatic. We're going to be less worried about being I/O bound, I think, in the near future. So memory bandwidth bound, probably I/O bound less. So, 10 minutes to lunch, so I will talk slightly faster. Most of our science requirements have stayed the same since I talked to you last year, with, of course, the slight perturbation, which is actually huge, of the increasing inroads of AI, not just in science, but in all the things around computing. More on that in a second. So we've finally gotten some parts where we can look at things where we can scale memory bandwidth up and down, both because there's some HBM parts, near to market at this point that many of us have. Not surprisingly, about half the workload is seriously memory bandwidth starved. Somewhat surprisingly, about half of it isn't. But we see everything from 0 improvement for things that were not memory bandwidth bound to more than 2x on the chip you all know I'm talking about. And so And I will say that's even though that architecturally, I think we're only getting about 50 or 60% of what the HBM could deliver because the cores can't consume it fast enough, which means there's some tweaks to happen in the fairly near future on that. But even then, we're seeing doubling. It is hard to say in general terms what kind of codes are memory bandwidth bound. I just picked two of our more earthquake-oriented seismic codes because that's most of our sort of open source workflow. But one more than doubled and one got 15%. So making generalizations is somewhat complicated on these things. But those endpoints are rare, but what we're seeing is no tuning, no code changes. Again, as you start to catch up to memory bandwidth of GPUs on CPUs, it does make a difference. And I would say that our GPU fraction of codes, and this conference is no exception, is getting better. We're seeing more and more GPU usage that works pretty well. But there's still a lot of significant holdouts. So I'm not ready to say we can just move everything there. Because we're just not there yet. So I would make one observation that we have noticed is that when we're looking at bandwidth load, we also continue to look at porting to GPU, as I mentioned. And a somewhat underappreciated factor here is the sort of non-linearity as precision goes down. I don't entirely understand why it's this good, but if you look at the way precision decreases, and Hopper H100 is now public, so I took those numbers. Not surprisingly, FP64 and FP32 have a 2-to-1 ratio because that's how we've built multipliers since, for those of you who majored in the right forms of engineering, sophomore year in college, when you design your first multiplier, you get 2-to-1 with half the bits. But if you start looking at these tensor operations, right, which doubles your 64-bit floating point, you notice it's a little better when you get to 32-bit tensors, right, where we jump from 67 teraflops to 989 in single precision, because needless to say, they're optimizing for AI workloads. And when you get to like 16, it's ridiculous, right? We're at 2 petaflops per card in H100. And that's for the current H100s, right? Nothing future out there, right? Petaflops per card. And more if you do 8, but you can't be sold on 8. So at some point, you're just guessing. But maybe we need to spend a little bit more time on, can we use mixed precision matrix ops given that there's a free 30x improvement in hardware performance when we hit those things. So certainly worth remembering that that's out there. And that actually leads to one of my other thesis points here, that is the AI market's going to drive the hardware, and we can use it or not use it. So, and actually that's the slide, so that's convenient. So, I would say at this point, we don't have nearly the sway in HPC with the vendors or the NRE budgets, which we at the university space have never had, but the DOE has a lot of, to substantially customize designs the way that we used to, right? And Dan Reed and Jack Dungara, I should have put the citation in, but forgot to get back to it, recently put out a very eloquent argument on this in their latest paper, which is called something like HPC Forecast Cloudy and something, because they wanted to talk about hyperscalers. But from my perspective, every part we're going to put into a new machine is going to be either one, built with hyperscaler customers in mind, or two, built by the hyperscalers, which is increasingly a part of what we see, because nothing else is going to survive the market, at least in the server side. Desktop parts, maybe not. So either the big guys buy them or the big guys build them. And we're going to have to continue to exploit some of that the way we have in clustering for a long time, of sort of using commodity things. So we probably need to refocus some of our efforts on exploiting things like matrix ops at lower precision and object stores and things that are built for that marketplace, because we're going to get stuck with them, whether we want to or not. So we might as well be good at it. So I did want to mention one last little vignette, a couple minutes to go here, between lunch. Always fun. So I did use this slide last year, said there were sort of several big things sort of progressing through federal funding in this. And as it turns out, I've got to leave in a couple hours to get on a plane to DC, because we're actually putting out the report tomorrow as the official launch of the National AI Research Resource, which has the unfortunate acronym NAIR, good for hair removal and fast AI, which is more useful than some AI. But anyway, and then the task force is NAIR-TF, which is even better. But yes, in January, this was officially sent to the White House and Congress, and so the sort of public launch of it is tomorrow. And it recommends a multi-billion-dollar investment in AI compute, which should have good bipartisan support, which used to mean it would make it through Congress, but now nothing means anything will make it through Congress. So, and I'd actually put this next slide together because originally I was supposed to moderate a panel of senators and congressmen talking about this tomorrow, and then the House scheduled a vote during it. So that sort of cut down on the congressmen that were available. So, but I was going to let them give their answers to why the U.S. should invest in AI. But I thought it'd be better if we just asked ChatGPT why the U.S. should invest in AI. It's probably roughly the answer that most congressmen would give, except a little more polished if you read it. So, you know, and it does. I've used it on some reports you wouldn't want to know about that we use this for, but yes, AI, by investing in AI, the U.S. can remain a leader in technological innovation and maintain global competitiveness. It can have economic benefits. McKinsey estimates it's going to have a $13 trillion economic impact. You can just hear a politician saying this stuff, right? So it'll help a variety of societal challenges, blah, blah, blah. In conclusion, to be, you know, looking towards the future, economic leader, motherhood, apple pie, invest in AI. So so actually, it's not the engineers' jobs I'm worried about replacing with AI, but if you're a consultant or a politician, you might want to get worried about this. But so with my last minute or two, ChatGPT can be spectacularly wrong, and you can fool it, and it's got all sorts of problems. It's also 3 months old, but you know what our codes look like 3 months out. But what does this mean for us actually in HPC? So first of all, let me just say that if you're trying to separate AI and HPC, that's just foolish, because AI is at the you know, peak of ridiculous hype and momentum, and more importantly, funding, and HPC has less of all of those. But it turns out it's all still multiplying matrices, right? And you know, they're about to have a big, you know, revolution when they figure out all their matrices are sparse. If only somebody had done that before. But if you do HPC, you should just start saying AI and HPC. So, you know, change the conference title, Energy High Performance Computing / AI Conference, and we're good to go. But seriously, it is worth thinking about how this can change your job now. So I promise 2 minutes, 18 slides, but 2 minutes. So this is a task we can all do. Well, again, if you majored in the right engineering, you can do this in a couple minutes. But if you use ChatGPT to write your code, so here I asked it to write me a matrix multiply in C. And it says, here's the matrix multiply, here's what it does, speaking of code with documentation, here's how you'd call it, and the resulting matrix C will produce the matrices A and B. It's correct, as far as I can tell. Okay, that's trivial. Convert the function above to use CUDA. Gets a lot longer. It's also compilable. There are multiple slides here because it's CUDA, so your 5 lines of code is now 40. But then I took this code down, uploaded it again later in a separate session, and said, convert it to HIP to run on an AMD GPU, and it worked. And then I said, rewrite that HIP code into data parallel C++ with SYCL, so it'll run on an Intel GPU. And it did that too. Now, obviously, you can't put a whole application with 100,000 lines of code in this and get it to work right. But if you can go sort of function by function, and you can just do this and then fix whatever minor bugs crop up in it, you're going to be a lot faster than porting the code from scratch, right? And so it's not to the point. It may get there, right? As Jensen Huang at NVIDIA loves to say, it's software that writes software. But we're getting to the point where if you're programming and you're not using it, it's sort of malpractice, right? Because you can go so much faster if you throw some of this stuff in. It even makes me a competent coder again. And by the way, yes, not only does it have all the CUDA code, it says what runs on the GPU and what doesn't, and again, the resulting matrix C will contain the products of A and B computed on a GPU, right? So it does a sort of remarkable job for code, and you say, well, what about our sophisticated scientific library? So can I multiply matrices with PETSI? The first slide doesn't get out of the definitions, but yes, it'll write you PETSI code too, and just about any other well-known library. And it does a not terrible job versus, say, hiring a programmer to do the same thing. But like I said, at this point, you need humans programmers, but you're faster with ChatGPT. And so it's great for program productivity, but really my job is to support HPC users, right? And it couldn't possibly do support things, right? So yeah, it totally can. So So I asked it how to use the API that we have at TAPS, and it said, and by the way, this is the raw, just free on the web model, not trained on any of our data. It says that TAPS is the Texas Advanced Computing Center API. It says it's a RESTful service that'll get you to the Slurm scheduler, the STAMP2 supercomputer, the file transfer service. To use it, you need to get a key. Here's an example of how you might call that, and to use that API with a key, and spits that out. And by the way, because normally it does all this in Python, but because I previously asked it questions about C, it speaks the language of old people and wrote it in C for me. Without me actually prompting it, because it knew that's what I was talking about. So but if you just go in on your own, it'll give you Python code to do this. But you can say, write it in Fortran, and it can actually do that stuff. Maybe not REST APIs, but yes, how to get the, all this is actually correct. It points to the right documentation. It's surprising. I asked it, how to use Jupyter in one of our civil engineering projects, Design Safe. Completely correct. Better written than a larger slice of my staff than I'd like to admit. The correct URL. So, at this point, canceling jobs in Slurm, yeah, tell you how to do that, right? So we did 10,000 tickets last year, 9,659 tickets last year. There's a lot of staff time invested in that, right? I am not ready to give this back to the users for the next slide's the reason, but I want to give this to all my consultants instantly along with the ticket when they do it to just see if it's, maybe I should just send this. Is it right? You still need humans to check it because occasionally when it fails, it will fail spectacularly because I asked it, can you use open on-demand attack? And the correct answer is no. We don't support it, but it has great details on how to do it, including made-up URLs to the documentation. So I thought that was fairly entertaining. So I do feel like we've reached a milestone in artificial intelligence, because by the way, if you ask it math questions, it's fairly bad too. So we've now built computers that it can both lie with confidence or be wrong, but be fully confident, just like a human can when they are wrong. And they're bad at math, which is the thing we built computers to do in the first place. So great, now we have computers that are like humans. Like the humans weren't annoying enough. So anyway, I miss when your code would just segfault instead of making up URLs for you. So we'll call that the good old days. But also for admins, this is slightly wrong, but it's really close, right? Can I query Lustre to find out how many files a user has on a specific object storage target? Yeah, I can answer that question too. So fairly niche questions without actually training it on any of our stuff specifically. So just to wrap up, because I know I'm out of time, it might be worth thinking about how large language models are going to affect your job, right? And it may not be that we're going to put AI into the full wave inversion or into the reservoir model. It may be we're going to use it to write the code to do it, or use it to help support users to do it, or pick the architecture to do it. And I want you to think about the win here for those of you, who run HPC groups and are in the business. One, you're going to be way more productive if you use it. Two, do you have any idea how much computing ChatGPT actually consumes? The rumor is the current model's running on about 6,000 GPUs. It eats about $3 million a day in cloud time, $1 billion a year. So not only will you be more productive and you'll make other people more productive, they will be forced then to increase your budget. So we remain indispensable, at least until next year's conference. And with that, I will stop there. So thanks very much.
Any questions for Dan?
So you're right that AI and HPC has been driving us to lower precision for many years now. Do you see that we'll make a U-turn at some point, given that AI will reach, they'll ask for explainable AI, they'll ask for physics-informed AI, and the resolution will say, we don't want to get garbage at lightning speed, speed of light. But
Yeah, it's a valid point, I think, particularly around the explainable AI, right? This notion of black box models, although we do trust humans for some reason, who are black box models that produce wrong answers regularly. So, case in point. I'm not sure that the U-turn in AI around will actually result in higher precision because, you think about deep learning algorithms anyway, right? It's these very sparse connected networks. And essentially, the only thing they're representing with a lot of those numbers is the strength of the connection, right? And if you have a few hundred or a few thousand values, that basically is enough to tell you is this one connected to the next one at the proper strength. So explainability might come from, physics-informed AI and backtracing as to how it made assumptions on the data it has. It may not be driving precision up, right? ChatGPT is actually a mix of 16 and 8 bit for most of the inference work that it does. So I do think that U-turn is coming. I'm not sure it's going to drive precision back up. And again, which means I'm not sure we're going to get better 64-bit circuits for our stuff, so, unfortunately. Yeah.
So,
yeah.
Is it on?
I can
It's
hear
working
you.
okay? Hi, Dan.
Hey.
Your slide about memory bandwidth and its impact on applications over a wide variety of fields. Do you guys have an understanding of how close people are to the memory roof line and how that sort of affects how much they need memory bandwidth, or rather what the impact of just sort of crudely increasing memory bandwidth is?
I talked about this some last year, right? We have 20 codes that we're using, 20 science problems that happen to use about 20 codes that are driving our decisions on the next machine. And we did roofline models on all of them to get started. Very few are actually close to the ideal memory bandwidth bound. A lot of that is just sort of artifacts of the code, right? So we're still, even with more memory bandwidth, we're just moving them a little closer to the line, but still not there before other things get in the way of performance for the most part. But I would just say from the benchmarking on those 20 and from the roof lines we've looked at, one is a lot of them have a lot of headway under the roof line yet, in both in terms of memory bandwidth and everything else about the code, vectorization, et cetera. But at least half the workload looks like it has a pretty significant memory bound factor, I would say.
I think that's consistent with our experience at Oak Ridge as well. I'll also say I love your slide about utilization and uptime and all that kind of good stuff. I'll arm wrestle you. We'll put up Summit's stats. I think they're very comparable, almost probably to two significant figures. I think they're the same number. The only difference being that our number of sort of quarter-sized jobs and bigger, instead of being 25%, is 50%. But
Yeah.
that's
Well, you guys get more credit for that
that's
stuff
a
than we
function
do.
of policy and,
Yeah.
and a selection effect more than anything.
Mine is I have too many faculty and review panels who I can't say no to.
Absolutely,
So,
right.
yeah.
It's a different
Versus what you
pool,
see,
even if
yeah.
there's strong overlap. Yeah.
Yeah. Get their own frontier. So.
Hey, hello. I'm Jay from CGG. So I just have a quick question. So as your slide mentioned, there's the one job maybe occupy the full system, the full resource of your system. Like, how did you guys guarantee the job's running without any issue in 24 hours or even more? Yeah.
Without a failure? Yeah. One is, so when I say full system, we actually do 8192 nodes. And we have 8300. And the reason for that is you pick the best 8192 to run the job at any given time when you're running at that scale. I bet Bronson had similar experiences, right? So if we take any node that is weak in any way, that's showing any flags, and you take it out of the way, there are still in those big runs, not surprisingly, I don't think this will surprise anyone, right? Killing the file system, I/O-related issues are the #1 thing that will kill a big job. In that 10,000 user tickets, the one ChatGPT probably couldn't answer because I can't turn on the profanity mode as well. But somebody saying, well, my individual runs take more than 3 million inodes, so I need more than that because I need to generate more than 3 million files in an individual run. And it's like, well, or you could not do that, right, is the correct answer. So, because that's a terrible idea. So So I/O is our biggest weak point on those jobs when we see failures. One of the reasons we set aside the machine to do that is a lot of the times finding those weak nodes is you need to launch it 2 or 3 times. If it makes it through the first 20 minutes, there's a fair chance it'll make it through the 24 to 48 hours we'll give it. And we don't ever give them more than 48 hours because then your probability of a hardware failure gets too high. You got to checkpoint and restart. But why we don't run it through normal batch queues at bigger than 2,000 nodes is, if you haven't launched the job at 4,000 before, it's probably not going to work the first time, and you're going to need to go fix something and relaunch it right away. And draining the queue like 4 times while they're debugging that is amazingly disruptive. So we just give them the system quietly in more or less an interactive mode and say, launch it till it starts. And that helps a lot with reliability on those.
Thank you.
Hi, Russell Jones, Total Energies.
Hey.
You mentioned you're using a BGFS instead of Lustre. I'd like you to kind of talk a little bit more about why you guys chose BGFS and what y'all's experience has been with it.
Yeah, it's been pretty good. And so, I'm the director, so I'm not really hands-on with BGFS that much. My measure is how often I have to talk about it at lunch with my systems guys, and I hear about luster problems way more than I hear about BGFS problems. So if that is a metric, then it's been good. I will say that that system is only like 750 nodes, like I said, a few tens of thousands of cores. So we're not stressing it nearly as hard as we've stressed luster, on the 8,000 node, 6,000 node fabrics, right, that we've put against it. But so far, concurrency, scalability, performance, all pretty good. We have found a couple little bugs, corners of POSIX compliance, where things don't work the way that you think. They've all been pretty responsive in getting those fixed. I think we just ran into 2 issues with Linux ACLs and crazy stuff like that. So, it's been pretty good. I will say, it's now getting pretty easy with object technologies to just build the global namespace out of NVMe devices. And we may not have quite as much dependency on file systems in general as we did, because roughly the entire industry is working on global namespace for NVMe. There's like 8 options to pick from. VAST, Weka, next gen from TDN. There's all sorts of things out there. So, so we're looking pretty heavily at that moving forward. But yeah, I can. At least up to 1,000 nodes, I feel really good about BGFS as a solution. So.
I appreciate just a little comment, having that measurement of how often sysadmins complain about it. It's a great measurement.
Yeah. Well, Tommy Minyard will be here, I think, tomorrow, certainly Thursday for the tutorial, who actually runs all this stuff day to day. When we're both in town, we try and go on lunch every day, and luster with adjectives is a very common start to lunch. So part of that is the scale we beat it at, and users who want to do things like create more than 3 million files in a single run. So.
Great job, Dan, on making it all different, so different from last year. Great new content. Speaking of workloads, are you seeing?
Got to have a new show every week. It's a thing. So yeah.
It was great. So speaking of these workloads, are you seeing, in addition to the classic HPC and some of these AI workloads, are you seeing graph analytics workloads starting to hit your systems at all?
Not at really huge scale. I think Gary's talking this afternoon. He might have more comments on that from the Los Alamos perspective. I have seen, and one thing I didn't say about AI is, and I saw somebody's tweet on this that I thought was future insightful, which is the superpower of AI will be turning unstructured data into structured data, right? Because even most of the work in AI is cleaning the data, and it's amazing at that. But I have seen just at small scale, we have a lot of users doing, using the GPT-3 API to pull information out of files, and the first thing you do is take all your text files and load them into a graph database to do that. So I've seen some of that at small scale, but nothing at like the big system scale yet. But certainly, yeah, had a conversation with somebody about that problem a couple weeks ago. So.
Dan, thank you very much for coming to
Catch me at lunch. Thanks, Steve.